Myself, Srinivasan, working as a faculty in the Department of Mechanical Engineering at Sri Shumar College of Engineering and Technology. The last lecture discussed about shallow autoencoder and deep autoencoders. So where we focus mainly on the representations and reconstruction of the input image, reconstruction of the latent representations. And we have in the autoencoder, we have two parts. One is encoder part and one is decoder part. Encoder part will take care of the representation rendering and decoder part will take care of the reconstruction part. Okay. And that on the shallow autoencoder, we have only one hidden unit, whereas in the deep autoencoder, we have more than one hidden layers. So that is the reason we can able to understand the complex representation, complex features against. Okay, so this thing one can understand in deep autoencoder. If you have image like if you have input if you have input in the form of image, so we have to flatten those the pixel values, and when you feed into deep autoencoder, it is highly impossible, or it is to some extent it is very complex to understand the features like shapes and edges and everything, means like edges, textures and everything. It is very difficult to do it in the deep autoencoder. So not to have that, we move on to a convolution autoencoder, and to remove the noises from the input image, then we can work on denoising autoencoders. So these two remaining autoencoders that we are going to see too. If you look at this autoencoder, and we have this input image 8, and we have the encoded part, and this is encoded part, this is a decoded part. So in the encoded part, what we are doing here is that we have the convolution and pooling operation will be done here, and finally we have this latent space representation or latent space representation, and from the latent representation, and we can maximize the sampling, and that is called decoded part. Okay. So in that, if you look at this input image, this is 28 cross 28. Then when you do convolution and pooling operation, and we'll use this filters, and filter size will increase, and it will try to capture the important features in the input image. Then obviously what is happening that you are trying to get the important informations, important features. At the same time, we are getting the reduction in the spatial dimensions. So you could see from 28 to 7 in the latent space. Okay. So once you have the latent space, and what you have to do is you have to maximize the samples and maximize the spatial dimensions. And we are doing this upselling techniques. We apply the upselling techniques. And when you go for upselling techniques, and we'll have some sort of artifacts that can be controlled by convolution operations. So what we are doing in the decoded part, we are doing the upsampling as well as convolution part, and finally we get the reconstructed image. Okay. So in one shot, I can say we have the input image, and we have the convolution and pooling operations, and as a result, we'll have that sample size of 7 cross 7. And once it is once you have that reconstructed, once you have the latent space representation, and we move on to upskilling, where we get maximum spatial dimension. And then to remove the artifact, we go for convolution operations, and finally we will end up with reconstructed output. So this is the way it works in the case of convolution autoencoder. So it's basically we work on convolution operation. That's why it is called convolution autoencoder. And as I said, when you use this without convolution operation, we will lose the spatial information. And when you go for convolution autoencoder, we will end up with edges and textures and share and everything. Okay. So this is a feature map that we get in latent space. There are 7 into 256. So then we can decoder, we go for the upscaling and transposed convolution operation, and finally we end up with reconstructed image. So this architecture is this. In the encoded part we have pooling and convolution, and the decoder part we have upsampling and transposed convolution operations. So when you go for the upsampling, so when you go for the upsampling, and we have different techniques to upsample. Yes, here we are trying to get maximum spatial information. We are trying to increase the dimension. So what we are doing here is that we have the two techniques called one. We discuss about a couple of techniques that we work on nearest neighbor subsampling and bed of names. So basically, we have this X is our input image. This is the scaling factor tool. And what we are doing here is that in the nearest neighbor upsampling, we take the values of the nearest neighbors will occupy the corresponding pixel value. So if you look at this, is here we have 1, and the remaining distance is the scaling factor is 2, and it's a 2 cross 2 matrix. And what we get here is that this 1 comma 1 1 and 1 1 here. So totally we have 4 elements. The second element, if you look at this, here we are doing two scaling factors 2 cross 2. Then finally we end up with 2 and 2 then we have 4 elements. So finally what we have done, we have increased the size of the image. Okay. So we have repeated the values basically here. In the bed of names, we have the 0 intersection, and instead of putting the values, we go with the 0 values. So that is a one way of going for upsum. And the second technique that we can work on is transposed convolution. In transposed convolution, we have artifact, but anyway, in order to overcome that, we can go for combination of convolution and this one. And before that, we will discuss about transposed convolution. In transposed convolution, we have this input image. This is a flip kernel. Okay, so instead of 1, 2, 3, 4, this is a kernel. When you flip this kernel to a 180 degree, okay, so what will happen? We end up with this kernel, and the output size is going to be, because we have 2 cross 2, then it is going to be 2, and the kernel is also is 2, and totally 4. We have 4 here minus 1. The output is going to be 3 cross 3. Okay. So what we can do is we have the 2 cross 2 input image, and if you look at this first element A11, and in that we are going to multiply the values of in the A11 we multiply the flip kernel. We end up with 4, 3, 2, 1. Okay. So that is for the first position. If you look at the second position, there is 1 comma 2, and we have this again when you multiply with this flip kernel, we end up with 8, 4, 6, 2. Okay. Similarly, you do for remaining position A1, A21 and A22, then what will happen? We have this 3 by 3 matrix. So what you have to do is, then you have to multiply. You have to add all the matrix that we have got from the respective positions. We'll have this output. So that's why it is called 3 cross 3. Output size is 3 cross 3 here. And when you do this, basically when you do this operation, we get this checkerboard artifacts. So this is an example for that kind of scenario. Okay. So that is a disadvantage of getting transposed convolution. Here we have some sort of some sort of noise over here. And what we can do is we can combine this upsampling technique as well as convolution operations. Basically, can we do convolution operation? We'll have this smoothing. So what is upsampling? But we can use this nearest neighbor technique. Okay. So what we have done here is 1 comma 1. I mean, in the place of 1, we can replicate the pixel values 1 1 and 1 1 in the place of area 1 2, and we can replicate here. And if you do all these things, and finally we end up with this upsampling. And once you have the upsampling, this is a flip kernel. And when you multiply these, and finally we end up with this new value for the particular position. Okay. So what I have done is this and this we have multiplied, and finally we got 10 values. And similarly, we have to now once you do the convolution operation, you have to slide. Then we have to take this second outer sliding one and we get this value 1 comma 2 1 comma 2. That has to be multiplied with multiplied by this kernel 1, and finally we get this 40. So if you do this and you will have a separate matrix, and that will enhance the quality of the input and quality of the output. So that is the advantage of using conjugation autoencoder. So when you move towards denoising an autoencoder, and what we do here is that we remove the noise from the input. So similar way what we have discussed in the conjugation operation, and the same thing we do here, but here focus is mainly on noise selections. Okay. So where in traditional autoencoder, what does it? Basically that it tries to get the latent space representation where we get the important features, and that will be again reconstructed from the latent, and the output is going to be the reconstructed one from the latent space representations. In this here we get when we have this noise image, and finally you get, when you do this denoising autoencoder, finally you get that clean output. Okay, so that is the advantage of this. So in previous case we have input and we have noise over here, and in case of denoising autoencoder, we have this noise, and finally we get clean output. Okay, so in the traditional one we get some noise in the reconstructor one, but here the input itself is a reconstructor. Input itself is a noise, and finally what we get is basically better image that has been derived from the input one. Okay. So that is the way it works for the denoising autoencoder. There are certain limitation in autoencoder, and basically we can't generate a new image, and we can't exactly work on learned features. I mean, we get features, but it won't give the proper shape, thickness, many informations. So whatever you have, it is going to be, it will be replicated, but it doesn't have any semantic representations, or the features are not exactly interpretable, and there are many things one can get from autoencoder. And this information, whatever you give, and you have the reconstructed one. So that's the reason we don't talk about more of classification, prediction, and so on. And as I said, this cannot give you new samples. So whatever the image you have, that will give you the, and then will give the whatever the original one you had. Okay, that is the advantage of that is a way it works out. So you can't generate a new samples. Okay, so because of the unstructured space. Okay, so whatever that you get in the output is basically unstructured space. So that cannot generate any new samples. That can be done by variable autoencoders that we are going to look at in the next class. But that is a disadvantage of using traditional autoencoders. So when you see this overfitting issues and all, and if the latent space size is huge, then we'll end up with overfitting issues, and we don't use any regularization techniques. Okay, so that is the advantage of the when you have this latent space is huge. So when you have this small, and that what you have done is basically excessive compression, and excessive compression will result in high concession loss. Okay. So these are the limitations that we encounter in autoencoder. So in this next class, we will discuss about variable autoencoder. Thank you.